Recording and
Okay, welcome everyone. Pleasure to have you here, and sorry for the short delay here. We entered the topic of the electronic partition function on Tuesday. Are there any questions so far? So just to recap, we went through the various modes, energetic modes the system can populate, right? Particular translation, rotation, vibration, and now we are in the electronic contribution. Now this list could continue, right? You can imagine external effects. We can imagine spin effects from the nuclei, for instance, like you would measure it in NMR, right? These are also modes. We will not go through this exhaustive list of all possible modes in this introductory course. So we restrict ourselves to the most fundamental ones only, right? If you get incredibly curious because of this introduction and you feel this incredible desire to study this further, then you're cordially invited to deepen this within your graduate studies, for example. Now, let's move forward to the part where we left. I believe we had the partition function for the electronic spectrum, and the hallmark difference of these modes in comparison to the other modes we discussed was that the gaps between the states, the gaps between the eigenvalues of the electronic Schrödinger equation are so large, right? Much larger than in the other cases. So then rather than trying to approximate the partition function, the sum over states, by a continuous integral, we just crudely and brutally truncate the whole sum after just one term, or maybe two. Okay. Of course, if you then go to some obscene regimes, like in the sun or in some reactor for nuclear fusion where you have plasma flying around, then maybe that might be a bad idea, right, to truncate after the first term. So beware. But for your average organic chemist, that should suffice. Now, I highlighted this example shown here of how our intuition is typically or traditionally trained towards the ground state, right? So these kind of geometrical ideas we have on how atoms arrange in space and so on, that usually refers to the electronic ground state. Now, as you go to a different state, you have completely different wave functions, all your rules change, right? And so what might seem like a transition state, for instance, in this case, the proton being completely out of the plane of the molecule, can be the geometrical minimum in the next excited state. So we stopped at the expression for the averaged energy, the internal energy contributions of the electrons to the thermodynamic internal energy, right? And this was this expression, and we basically saw that we recovered what we've put in, namely an estimate of the electronic energy to the formation energy, something you can get experimentally and in the literature. Now, if we then take this result and differentiate it once further, we would obtain the heat capacity, and this is at constant volume, right? So the isochoric heat capacity. This is the regime where we start our thermodynamic discussions, and in following classical thermodynamics, you can convert those then to isobaric conditions, where you have something that resembles the situation in the lab at a certain altitude. We always have the same pressure, and you let the volume breathe. Right? Now, this heat capacity contribution is only for the electrons, so we call it CVE. And this must be the derivative of U with respect to T. And I have here for U my electronic energy, and that one will not depend on the temperature of the atoms, right? So that's sort of fixed. And so this heat capacity contribution in general is very small, or zero. We have an entropy contribution where we can make use of one of the expressions for the entropy, where we simply insert for the internal energy the electronic version, right? So this was one of the expressions. Now we use the electronic partition function. And if you insert that, you have the logarithm of G0 minus R E0 over KBT. And for E0 again, we use our delta F U0 over NA. So if you insert that, you find that this whole thing is R delta F U0 divided by R T. These two R's cancel. The delta F U0 is the UE. So you're only left with the middle term. The entropy is the ideal gas constant times the logarithm of the degeneracy of your ground state. And this is, of course, the molar entropy. Right? We actually have seen this already in the beginning when we introduced the entropy. We briefly talked about the two-state system with equal probability. And that's what a degeneracy is, right? Degeneracy means you have same energy value, so you have same probability, right? So you might remember that from the coin flip. Now, most molecules G0, your electronic degeneracy is equals to 1. Okay. Now, one example of an exception. So there are exceptions O2 has G0 equals 3. Okay. And so as you go to open shell systems, to radicals, to transition metals, and so on, this becomes very frequent and nothing unusual. Right? So you have to be a little bit careful with the above statements. Right? It actually could represent some bias. Now, you should have heard about the atomic term symbols. This is, of course, an introductory in organic chemistry. When you discuss the periodic table, you use these term symbols to represent the electronic configuration of the free atom. Now, the statistical mechanics of free atoms is boring, but for diatomics, things start to become interesting. And there is an analogon for the atomic term symbol. Right? So for diatomics, we can refer to their electronic state by using the symbol capital gamma, which is a generalized Russell-Saunders spin orbit coupling term symbol, just as L is for the free atom. Okay. So nothing to be afraid of. It basically tries to put into a digit characteristic features of the wave function, the electronic wave function. Okay. So let's consider some examples. Here's the species or system, depending if you favor biology or physics. And then the symbol, and we denote Ts plus 1 for the spin multiplicity. Here on the left top super index, then the gamma, then we note the degeneracy and the level, the electronic level. And we also introduce, again, a characteristic electronic temperature, capital theta, in Kelvin. Okay. So we have these 5 columns here, and we begin with the N2 molecule, the most dominant molecule in our planet's atmosphere. Here, the symbol would be 1, so multiplicity 1, a big sigma, so in other words, think pi, think something like a sigma bonded shape, plus and G, right? So this is the symbol, plus referring to symmetry, and G as well. So G stands for Grade, which is even, right? So there are even and odd functions. So this will be the ground state. So for state 0, you have this, and the degeneracy is 1. Right? Now, as soon as we go to NO, right, so you add a proton and an electron to one of the nitrogens, things become really interesting. In this case, you have more something like a pi bond, right? This is the entire electronic wave function, right? So not just one orbital. And then there's a 1/2. The degeneracy is 2, and the ground state is 0. And now we have another state, 3/2, and the degeneracy is 2. And this is the first excited state. And now the characteristic temperature for this is 178 in Kelvin. Now, that's a very small number, and it's indicative that in this molecule, the first excited state is not far away, but it happens to be quite close to the ground state, right? So we'll revisit that again in a minute. Now, to think about NO, you can draw a Lewis structure formula, right? And now you see here the unpaired electron, and that's indicative of trouble. So not so surprising in that regard. Now, the precise meaning of these indices, you don't have to worry about, right? We just use them to label these functions, okay? To label these wave functions. So this would be the topic of an advanced quantum course, electronic quantum course, with the spectroscopy of these species, where you would learn more about that. For now, we just use these as symbols to distinguish these different states. And we can also, of course, consider O2. In O2, again, you have a sigma wave function, this time with minus and even, and 3 here. And here now we have a degeneracy of 3 in the ground state. And let me also draw the oxygen molecule, so you could think about it as something like that. And we also have a second state, capital delta 1. This is multiplicity 1 or degeneracy 1 in your first state. And in this case, the characteristic temperature is 11,650, okay? So you see 100 times more than in the NO case, right? So this is what's much more typical, huge electronic gap. And now F2 as a 1 sigma plus G first state, ground state with degeneracy 1, okay? So this is how such a picture could look like, coming from spectroscopic literature. And the energy gap between ground and first excited state is given as a characteristic electronic temperature, right? If we have a contributing first excited state, so if we cannot truncate after the first term, we can write an electronic partition function, which we have shifted by, so shifted by setting delta U equals 0 for the ground state, right? And that is simply saying that the exponential with the Boltzmann factor then becomes 1. And so you're left with the degeneracy for the ground state plus the degeneracy for the first excited state minus this excitation energy expressed in terms of the characteristic temperature over T. Okay. So if things turn really bad and you cannot truncate after the ground state and you have to consider the first excited state, then you can play this trick, shift your energy, and we want to now consider the case of NO for this situation. So example NO. Or before I continue, other questions? Yes, please.
First, what are the capital Greek letters stand for, like the sigma, gamma, and pi?
Yes. So thank you for this question. The question is, what do the Greek capital letters stand for? These are specific instances of a term symbol, this capital gamma here, which is this Russell-Sanders spin orbit coupling term for the wave function. So this describes the symmetry of the electronic wave function, okay? And so you can imagine different symmetries, a little bit like these MO diagrams, right? We like to talk about pi orbitals, sigma orbitals, and so on. So these are these analogous symmetry symbols. So if a wave function is being solved in terms of a Schrödinger equation, right, you will observe some symmetry in this solution, right? And you can use this symmetry to label this wave function, right? Now, that's, of course, not a quantitative thing, right? You're simply saying there's a positive part here in space, a negative one here, or a negative here and a positive here, right? So that's basically what this stands for. And so sigma stands for different symmetry than pi or than capital delta. Now, the upper left-hand index indicates the degeneracy here. And the right-hand indices you can ignore for now. I've just added them as to be more complete, right? But for our discussion, it's irrelevant right now. Does that make sense? It's an analogy to the atomic term symbols, right? For the atoms, you should have studied atomic term symbols, right? Where you can read off the spin of the atom, different electronic configurations, right? Does it make sense?
So when do we assign sigma, and when do we assign pi or delta?
So that happens when you do the spectroscopic measurement, right? And you try to establish how the wave function looks like, right? And then you can assign that symmetry to it, right? So in this course, you don't have to do this, right? This would be a more advanced electronic quantum spectroscopy course. Right? If you study the spectroscopy of electrons and molecules, that's where you should learn about this. Sounds good. Maybe first here, then there, yeah? Please go ahead.
Yeah, so the oxygen structure with the radicals, that would be the first excited state, right?
No. this actually would be the ground state. And the first excited state is what you would draw like this. Right. So oxygen is a reactive species. The whole word oxidation, that's where it comes from, right? And one of the reasons is that the electronic ground state happens to be an open shell state. Right? Now, if you ask me why, then I will refer you back to Schrödinger's equation. That's the solution that comes out of Schrödinger's equation. Yeah? And it matches the experiment. Okay. If you then still ask why, then we enter the question of why certain solutions to differential equations look like they look. You still had a question?
Molecules have multiple states, or like N2, like F2 only has one.
You don't, right? You saw Schrödinger's equation. It sounds like a cheap answer, right? But the intuition we have to build is around that, right? This is where the truth is. It's a complex equation, right? It's worthy many hours of meditation. Some people manage to develop an intuition, right? Others never. There are famous quotes saying, if you think you have understood quantum mechanics, you haven't understood it, or things like this, right? So this is why it's complicated. The good news is we can measure it, okay? And we can calculate it. So last week you've heard about ways to calculate it, right? So all these term symbols, I could get approximate versions of these wave functions from a density functional theory calculation, for example, and then do a symmetry analysis, and then I could predict which symbol, which gamma symbol should be used for those, right? And the symmetry analysis, usually once you have the wave function, to determine the symmetry is a rather straightforward exercise, and it's not rocket science, but okay, it might take more than 5 minutes also, but yeah. Sounds good. Any further questions on this? I know it's a lot, right, to take in, so I go slow and just stop me, and we can talk some more about it. It's when you hear this the first time, it's always confusing. So let's go back to this NO system. So basically, what you should think about when somebody says NO, you think about some E0. And then there's really close by, there's this E1, right? And that's exactly this kind of worst case scenario where in the last lecture and in the beginning of today's lecture, I told you this is extremely rare, never happens. We can truncate after the first term. And here you have the first exception to that rule. So NO's ground and first excited state are both low lying. So this means this corresponds to an isolated two-level system, right? So the second excited state then is far away again, right? Huge gap. So there's the characteristic temperature H nu over KB is this theta L, and nu is the frequency you would need to go from from ground to first excited state, and this is 178 Kelvin, right? So in wave numbers, this corresponds to a new E of 125 inverse centimeters, right? So that's more on the electronic, on the vibrational, typically in a vibrational mode, right? So very close by. Now, you have in both cases a degeneracy of 2, right? So G0 equals G1 equals 2. And that means there are 2 states in ground state and 2 states in excited state. Okay. Now, these states are, in terms of multiplicity, these are doublet states, right? So your multiplicity, your spin is the sum over all your ms, and you see here all electrons you can draw it such a way that one electron is over, so all the closed shell ones cancel out, and then you're left with 1 plus 1/2, right? So remember that ms is either minus 1/2 or plus 1/2. So your degeneracy corresponds to the multiplicity, and this is 2 times s plus 1. And so you have 2 times 1/2 plus 1 equals 2. So this multiplicity, this is a doublet, right? Okay, so this is spin determining your degeneracy, right? Your G. So you're given this, your partition function now becomes 2 plus 2 times e to the minus, and now we insert the characteristic temperature, and we have T, okay? So this would be the partition function, the electronic partition function for NO. So you can now insert this into the expression for your energy. And then you can now differentiate this further to get the electronic heat capacity. And in this case, this is not 0, but so you differentiate once more, but rather a function of temperature, which is extremely interesting. It's infamous in physics. This leads to what is known as a Schottky anomaly, anomaly, sorry. The Schottky anomaly. Okay, I'll show you what that is. If you do the differentiation, what you will find is that your CV becomes the ideal gas constant, the characteristic temperature over T squared. And so this is similar to the vibrational heat capacity contribution. So you can check if you find the same. You get the ratio between the degeneracies. In our case, it's just 2/2, so 1. And then e to the theta e over t divided by e to the theta e over t plus the ratio again, and the whole thing squared. Okay. So if we now enter the value for the characteristic temperature, we can plot our heat capacity as a function of temperature. And you've seen these figures of heat capacity versus temperature already for the other modes. And you might have noticed it always grows monotonically with temperature. Right? And the anomaly of Schottky was to realize that for the electronic heat capacity, this actually, there can be an exception to this, right? In particular, you can observe something which looks like this. Okay. So CVE in ideal gas constant units, T in Kelvin, and you will observe a peak at 74 Kelvin. Your heat capacity will be maximal. Okay. And the maximum should be roughly speaking at nearly half an ideal gas constant. Okay. And this behavior is known as this Schottky anomaly. And I don't think there's any other energy mode where you could have a non-monotonic change. So usually your heat capacity keeps on growing as you go higher in temperature, right? Your system will swallow up more and more of the heat. In this case, it peaks at this temperature. And this depends, of course, on your characteristic electronic temperature. And so it depends on the system, right? So for NO, but a condition is that you need this partition function of two close lying states. So whatever system you find where the electronic states are close lying, you should be able to observe a Schottky anomaly in the electronic heat capacity. If you don't, then you fall back. You don't have the second term in your partition function, and your heat capacity does not depend on the electronic degrees of freedom. Right? Now, of course, this was sort of hidden in the measured heat capacities, because you would only, when you do the measurement, you measure the sum of all the modes, right? You measure the vibrational heat capacity, the translational one, and then the electronic on top, right? And so this maximum, if you sum them up, then becomes like a shoulder, right? A little bump on top of what's growing monotonically, and that's why it was hidden. Only once you do the microscopic analysis of the individual modes, you actually see this being crystallizing out, right? So there's also a nice illustration of how the understanding of a more detailed understanding of the individual modes really helps in getting a clear picture of what's going on. Now, are there any questions on this so far? Seems good. Okay. One remark, 2 years ago, I gave the same lecture, the same course at UFT, and the large language models were just coming out. I queried GP2-4. It didn't know about Schottky anomaly. Now, I just checked once more. Now they know, right? So it's a nice illustration also. So they are clearly becoming increasingly more useful, right? So I don't know if you quick query who's using large language models for assisting with your studies. Anybody? I think you should. I mean, I would. Okay, who doesn't use it? Hands up. You don't? Okay. I'd recommend considering it. I think can really help. Also with finding textbooks, right? As an additional tool, of course, right? Now, we often get queried if we think this will impact education. I think, of course, it will, in the sense that it should make your studies much more effective, right? So it's a great assistant. When I was your age, I wanted to read up on something, I literally had to go physically into a library and search the journals. So they had shelves with printed journals, right? Like cartoon books. So you go in the library and then you have endless shelves. And so you look for issue number, I don't know, 10,044 in some shelf somewhere. On page 36, then is the equation you wanted, right? And so extremely hard to find, very, and now you have it so much easier. So, but anyhow, so just as a remark, let's conclude this chapter with this sort of summary where we can also note that there's a partition function for the spin, right? And that would account for spin orbit coupling, auto and para spins of the nuclei, right? So you could, for example, consider H2, right? There's auto and para H2, and it would also account for NMR and ESR, right? So if you are studying phenomena that involve these modes, right, you need that partition function. But we skip that in this course. I think you got the gist of how this works, right? So if you wanted, you can also study this yourself. So what we've focused on so far is really these 3n minus 3 minus 3 or 2. So these are our rotational, our translational, and our vibrational modes. For the translational, we had the particle in the box solutions. Here we had a rotational, the rigid rotor. So the Schrödinger solution for particle in the box, for rigid rotor, and for vibration, we had the harmonic oscillator. And the electronic, where we made simply use of truncations. Yeah. So this, in a nutshell, summarizes this entire chapter. I'd like to conclude today's lecture with this, and I thank you for your attention, and I see you next week.